a welcome, and I hope everybody had a great lunch. And thanks for joining us here today. I'm Bob Sivak. I'm the Senior Vice President of Business Development Operations at OCE, and I'm very pleased to be hosting this session today. So I'm going to read from my notes so I can do a nice, solid introduction here. Of course, this is an exciting session for me personally, because and I'm sure all of you are very interested in this topic. The physics and innovation, putting quantum into context, is the topic. So lots of buzz about quantum computers, sensing devices. This session is meant to share how scientists are exploring the nature of quantum physics to propel new fundamental insights.
Ladies and gentlemen, just another reminder.
Didn't I tell you that was going to happen?
Starting at 2:15, Pat Hogan, Vice President, Manufacturing Development Operations for IBM, will be presenting, followed by Betty DeVita, President of the MasterCard Canada. Please make your way to the Vision Theatre now.
Okay, sorry for that. I knew that was going to happen. I actually said that would happen. I predicted that. Without the help of quantum computing, I predicted that. So anyway, let me continue. It's my distinct honor to introduce our moderators for this session, Michael Duschenes of the Perimeter Institute for Theoretical Physics and Bob Crow of the Institute for Quantum Computing. Michael is the Chief Operating Officer at the Perimeter Institute. He has overall responsibility for the management of the PI, including short and long-term planning. Michael has oversight of the Perimeter Institute's award-winning outreach programs, finance, revenue generation strategies, including the innovative public-private partnership model used by the center, relationships with academic and research partners, communications, publications initiatives, attraction and retention strategies, IT, facility management. Boy, you do everything there. It's unbelievable. It takes us, at OCE, we have 25 people doing what you do by yourself. No, I'm just kidding. Including the construction of the Stephen Hawking Center at the Perimeter Institute and the administration of all scientific programs. Please welcome Michael. Bob Crow is the executive in residence at the Institute for Quantum Computing at the University of Waterloo. Bob oversees the overall management of IQC, including strategic and financial planning, government relations, communications, and outreach activities. Before joining IQC in 2012, Bob was Vice President at Research in Motion, where he built and led global programs, university research, market intelligence, government relations, community relations, and corporate responsibility. We welcome Bob. Okay, to get started and introduce the rest of the panel, I'd like to now invite Michael to the podium. Michael?
Thank you very much. Thank you very much, Bob. Good afternoon, everybody. Very nice for us to be here. Nice to be joined by my colleagues from the Institute for Quantum Computing. This afternoon's session is basically going to have 4 parts. I'm going to give you just a little bit of context, give you some sort of sense of how Waterloo has become a world power in quantum science research. We're going to get a little bit of a picture of the ecosystem that we live in Waterloo. That's going to come from Bob. And then the really interesting stuff is going to come from our 2 scientists, Damian and Martin, who are going to talk a little bit about the science itself and the incredible things that are on the horizon right now. So the story begins 1999. Mike Lazaridis, whom you know well, inventor of the BlackBerry, inventor of the smartphone. Mike has a vision. He believes that there's an opportunity to invest in a field of research that he feels has been very underappreciated, underinvested in, even though it has been extremely, extremely productive. Now, this has nothing to do with RIM. This has nothing to do with BlackBerry. This is Mike's personal interest, his personal philanthropy. He believes there's a massive opportunity for Canada to have a leadership role in the field of physics research. So why does he think that? He knows that every single piece of modern technology we use today has its roots in physics. You'll get a little bit more of a picture from our scientists about that. He believes this is an area where Canada can have a major leadership role, and he believes there needs to be very, very strategic investment in the field. In 1999, he founds Perimeter Institute. In 2002, the Institute for Quantum Computing at the University of Waterloo is founded. There you have our two facilities today. So in a very, very short time, Waterloo has two of the top centers in physics research in the world. On the left over there is the Stephen Hawking Center at Perimeter Institute, which we completed about a year and a half ago, doubling the size of the facility. That's now the largest theoretical physics institute in the world. On the right, the Mike and Ophelia Lazaridis Quantum Nano Center, home of the Institute for Quantum Computing and recognized as one of the leading laboratory infrastructures for research anywhere. Between Perimeter and IQC, there are now more than 350 researchers working in quantum science. More than $650 million have been invested in this area by the public and a private sector partnership. Has been extremely, extremely effective. And Waterloo, as I said, is now known as one of the world centers for research in this area. Not only do PI and IQC collaborate very, very closely together, but they also exist in a very, very robust ecosystem that exists in the region of Waterloo, and Bob is going to talk about that in a minute. One of the keys to success of these two institutes has been the ability to attract many of the top researchers from around the world. So this gives you just a little bit of a picture of the diversity. No recruitment by quota, always recruitment by target opportunity. Go after the very, very top people in the world. I'll point out a couple of them to you. On the very top right-hand corner, that's Neil Turok, director of Perimeter, one of the world's leading cosmologists. He's originally from South Africa. We poached him from Cambridge. Right in the center at the top, Raymond Laflamme, director of the Institute for Quantum Computing. A Canadian whom we brought back to Canada. He was in Los Alamos, came to Perimeter to be a founding faculty member and the director of the Institute for Quantum Computing. Two separate institutes. Perimeter is completely independent. The Institute for Quantum Computing works within the University of Waterloo, but it's the ability of these institutes to work very, very closely together, bring that critical mass of researchers working across the spectrum from basic research through experimentation that has accelerated progress so much in this field. As I mentioned before, we work within a bigger ecosystem in the region of Waterloo, and I'm going to ask Bob to come and talk a little bit about that now.
Great. Perfect. Well, thank you. Whoa, there we go. There's the voice of something. Thank you very much, Michael, and great to be back and see so many old friends in the audience and many colleagues from the University of Waterloo as well. So thank you for being here with us. The Waterloo regional ecosystem is truly something of marvel. I think we read about, hear about this all the time. And I think we learned a little bit at lunch from Steve Blank about what really goes on in such a place. We have an extremely high density of three things. One, knowledge creation from top people at our universities and our institutes. We have a high density of entrepreneurship, and we also have a high density of that crazy capital. And to that end, this region has actually been building industries for nearly 2 centuries. The industries that have been built in Waterloo include insurance, whiskey, sausages, zippers, rubber, smartphones, and enterprise software. And over the next few years, we are building a quantum industry to serve our region, our province, and our country. And the essential elements of those are, again, those same elements that Steve talked about in the luncheon session. It means we have the continuous, and no shortcuts, we have the continuous creation of scientific knowledge and experimental breakthroughs at the world's highest level. We have that in the theoretical and empirical mix that we find as between Perimeter Institute and the Institute for Quantum Computing. We see these meshed here as important, like gears in a fine watch. And that meshing is indeed important because it's not simply a matter of having a fine wall between theory and practice. Theory and practice inform one another and continue and result in some continuous development. But theory and practice, again, without a culture of entrepreneurship and without a culture of finance, are insufficient to build an industry. And that, as Michael has described, the culture of finance is kind of started by our mutual benefactor, Mike Lazaridis, and more recently, Mike and his partner, Doug Freegan, his original partner in Research in Motion, have announced the development of, or the creation of a $100 million fund called Quantum Valley Investments, which, along with sustaining investment by the province and by our federal government, mean that we have all the elements necessary, with the one exception of the entrepreneurial spark, okay, that are the necessary ingredients to build an industry. And where is that entrepreneurial spark? Again, it's from our broader infrastructure. Here we are in a relatively modest-sized region, but a modest-sized region that has that entrepreneurial spark and has the specific institutions that are supporting entrepreneurs and supporting people who do financing, the same way that our two institutions are supporting people who do scientific discovery and build technologies. We're very excited about the prospects of Quantum Valley. And in fact, we already have a couple of examples of startup companies, just like you would expect at the very beginning. They're early years, but many exciting things are here to come. But to tell you a little bit more about why and where it's going, we have two of our scientists, one from each institution. First, let me introduce, let me put your pictures up, guys. Dr. Damian Pope. Damian is the Senior Manager of Scientific Outreach at Perimeter Institute for Theoretical Physics in Waterloo. Damian is passionate about sharing the power, joy, and wonder of science with students, teachers, and the general public. He's involved in a wide range of projects, including the creation of educational resources, delivering workshops to teachers, and speaking to wider audiences. Damian created an in-class teaching kit called The Challenge of Quantum Reality that's now used all across Canada, as well as other resources contributing to the award-winning documentary called The Quantum Tamers, revealing our weird and wired future. Damian also regularly provides lectures and workshops on modern physics. He holds a PhD in theoretical quantum physics from the University of Queensland in Australia. And Damian's colleague on the podium today will be Dr. Martin Laforest. Martin is the Senior Manager of Scientific Outreach at IQC. Martin's role at the Institute for Quantum Computing, similar to Damian's, is to bring science out of the lab and into people's lives. He leads IQC's strategic outreach programs, including our prestigious undergraduate school on experimental quantum information processing, and the unique quantum cryptography school for young students, which is targeted at high school students. He also leads academic outreach for the collaborative graduate program in quantum information at the University of Waterloo. Dr. Laforest is actively involved in industry and government relations at IQC, bringing his scientific knowledge and experience to the discussion. A passionate advocate for communicating science, and shares his passions with audiences around the world as a guest speaker and lecturer. Martin was one of our first grad students at IQC, and we're very proud that he holds a PhD in physics, majoring in experimental quantum information from the University of Waterloo. So without further ado, I give you Damian and then Martin.
Okay, thank you very much for that, Bob. So I'm going to spend the next 20 minutes or so talking about something that's very dear and very passionate to me, and that's quantum physics. I'm going to be in particular talking about three things. The first one is why physics matters. The second one is what actually is quantum physics. And the third one really is about how scientists are starting to harness the principles of quantum physics to process information in very new and superior ways to any conventional means that are around at the moment. So something that's very, very exciting. First of all, why does physics matter? We're a theoretical physics institute. And so physics really is important for two reasons. One is it advances knowledge. And what do we mean by that? First of all, it sheds a little bit of light on the deep, dark, mysterious universe that we all live in, and contributes to the store of human knowledge. It also provides a foundation for many other sciences like biology, chemistry, geology, from kind of looking at things in a very different fundamental perspective. So more practically, physics is useful because it provides a foundation for future innovation. If you think of all of the gadgets and technologies that you use daily, and in fact, even all of the technologies throughout history, and you ask, where did they come from? Where did they ultimately come from? They ultimately come from some basic scientific idea, some new understanding and insight to the world that some scientist had, and that he or she applied. Basically, or some engineer, someone took that and ran with that and applied that to create something new that had never existed before. So in many ways, physics is kind of like a bedrock for innovation. So halfway through the 19th century, physicist James Maxwell looked very, very carefully about electricity and about magnets. And he realized that the two phenomena were actually intimately and very closely related to each other. Out of that, he came up with a deep, new, bold understanding of these phenomena. And then decades later, pioneers like Marconi actually used that to send information through the air, the first form of wireless communication. Now, all of us today, fast forward to the present day, use cell phones. There are over 1 billion cell phones, smartphones on the planet that people use to communicate via wireless communication. And you can trace back really the seed of that idea to James Maxwell about 150 years ago. Another example, Einstein. So the first couple of decades of the 20th century, Albert Einstein thought very deeply about space, time, energy, and matter, and came up with a radical new theory about how they're all related to each other. That was, of course, his theory of relativity. And at the time, it was incredibly abstract, and he had actually no inkling whatsoever that would have any practical application. But a couple of decades later, engineers working on a new navigation system, the GPS, or Global Positioning System, actually applied some of his ideas about time and built that into basically the ultra-precise timing mechanism that allows the GPS to operate and pretty much determine where we are on the planet down to within about a meter or so. And this was something that would have completely new, radical, never ever dreamt up by Einstein. So another example, quantum physics. So quantum physics is really the best current theory we have of the properties of the subatomic world, the tiniest particles known to humanity, to science. And the first couple of decades of the 20th century, Einstein, Schrödinger, Niels Bohr, a whole group of scientists actually came up with a radical new way of understanding how these teeny tiny particles behaved. That was, of course, quantum physics. A few decades or so after that, engineers looked and scientists looked at that to try to understand semiconductors and their electrical properties. And out of that came first the transistor, and then integrated circuits, the idea of sort of cramming multiple circuits onto the single chip. And pretty much every single electronic gadget that you use in modern electronics relies on the principle or the idea of an integrated circuit. So incredibly powerful idea. And this is an example. This is a photo on the right. It might not look by much, but that's the very first transistor. And the three scientists that invented that discovered it at Bell Labs. So what is a transistor? So you can think of that as an electronic switch. So just like a light switch can be on or off, so a transistor could be on or off depending on whether there's electrical current flowing through it or not. And if we're talking about on or off, then we can think of that as 0 or 1. And if we're thinking about zeros and ones, then we're talking the languages of computers. And so a transistor is probably the dominant, most prevalent component inside computers and all of these modern electrical devices that we use. Just inside your cell phone alone, there would be millions of individual tiny transistors. In fact, it's been estimated there are about 1 million trillion transistors on the planet. That amounts to basically 1 billion transistors for every single human being. And how it relates to quantum is that fundamentally a transistor is a quantum device. To build one, to understand a transistor, you need to understand the principles of quantum physics. So I should add that obviously modern electronics, if you think of that as an industry, that gets down to sort of trillions of dollars. It's been estimated that account for around about 1/3 of the GDP of the United States and other advanced countries. So much for kind of physics in general. So my area of research, quantum physics. What What is quantum physics? Really, the story starts in the start of the 20th century, where Einstein, Schrödinger, Niels Bohr, some of history's smartest minds, turned their attention to trying to understand the smallest known particles in nature, things like atoms, electrons, and protons. So just to give you kind of an idea of scale, how small is an atom? So what we have here is an animation. And hopefully you can see that well, but that actually starts with a gentleman, and he's basically standing on a picnic blanket. So that's at the scale of a few meters. And you'll notice there's a kind of a white square in that. And basically every time you see a new white square, we're zooming in by a factor of 10. So if we start playing the animation, what we do is we quickly get to the limit of human resolution, where we look at the different layers of the skin, and now quickly get beyond that, and we're getting up to individual cells inside the layers of the human skin. And if we go even further than that, what we end up with is the famous DNA double helix molecule. Basically now, 10 to the minus 7 meters, we're at the limit of the resolution of a regular microscope. So here we go even further, we're down at the level of DNA, and if we look at the individual molecules and the atoms that make it up, around about 1/10 of a nanometer, 10 to the minus 10 meters. That's about the size of a typical atom, and that's the scale at which quantum physics operates. So when Einstein, when other scientists looked at that scale, at the scale of individual atoms, 1/10 of a nanometer, what did they see? Well, they found out that the world operated in radically different ways to the ways that we're used to and we kind of experience in daily life. Some kind of people think of it almost as like an Alice in Wonderland type of world, where everything is topsy-turvy and everything is very counterintuitive and not what you would expect. There are when you boil down to it, two fundamental principles that govern the quantum world. The first one is something we call superposition. What is superposition? What we found out is that it seems as if the fundamental particles, atoms, electrons, protons, can actually somehow be in two or more places at the same time, something we don't experience in daily life. Now, this is a very mysterious phenomenon, and we don't fully understand it, but it seems to be what nature is telling us. And here you find this is an artist's representation of a single electron kind of spreading out and splitting up into many possibilities, existing in a so-called superposition state. So the other idea that kind of underpins quantum physics is the uncertainty principle. So historically in physics and science, we think of the idea of a scientist performing an experiment as able to kind of stand outside of the experiment and only not sort of alter it and basically interact with it in any kind of meaningful, disruptive way. It can actually observe some physical experiment and not alter it or change it or be some detached observer. But in quantum physics, what we find is that any time you're actually measuring or you're observing at a quantum particle, they're on such small a scale, they're so delicate that you necessarily disrupt it and you change it in an unavoidable way. And no matter how careful you are and precise you are with your experiments, you unnecessarily alter in a very significant way any quantum particle, an electron, for example, that you're looking at. And this is called the uncertainty principle, and it's one of the defining features of quantum physics. So we think it only operates at a subatomic level, but if we imagine that being blown up into ordinary life, you get some very, very strange effects indeed. So much for my kind of speed tour of quantum physics. I'd like to talk about my second point, and that is information. So this is a map of the backbone of the internet. What you can see there is these are all of the major undersea cables that carry all of the internet traffic daily. So that accounts to around about 100 million gigabytes of data every day. We are just bathed in information that permeates every aspect of our life, whether we're sending information or receiving information. So we really, truly do live in the quantum age. The information age. And if we dig a bit deeper, what we find is that we look inside all of this information. What we find, all of that is transmitted by tiny little packets of either electricity or little packets of light. So what that means is all of these are physical objects, so they're actually obeyed and the laws of physics. So ultimately, information is physical. So if we really want to understand information and how we can push the limits of what we can process and send and receiving information, then we want to turn to physics. And if you look at many ways, the history of the progress in information has been using physics to basically miniaturize smaller and smaller electrical components like transistors and to basically generate more powerful computers, so-called Moore's law. And there's an interesting thing about that. If you kind of extrapolate that to around about a decade or so into the future, what you find is that the components are so small, the engineers are so successful, you're actually going to find individual components, transistors, are going to be about the size of an atom. And when you get to the size of an atom, that's the ultimate roadblock for basically the kind of the techniques and the paradigms and the tools we've been using so far. Because when you get to the scale and size of an atom, then the rules of the game change. You're at the quantum scale, and objects, particles behave in radically different ways. And all of the current ways you've been using, kind of the techniques, just don't work anymore. So this might seem like kind of a negative thing, might have some negative connotations. And exactly that's what it seemed like at the start. But now what scientists have started to do over the last couple of decades is to realize this is actually a really great, huge opportunity. And so what we're actually starting to do is actually taking some of these seemingly crazy ideas from quantum physics, you can see on the left, the superposition and the uncertainty principle, and kind of combining with information theory, what we know about information, to actually create quantum information. And so that's when you're kind of sending, receiving information, you're processing information actually at the quantum level, using fundamentally different principles to any kind of conventional means. And what we found that when you can do that, you can actually do that in superior ways. You can perform information processing tasks like computations, which are absolutely impossible to do via any conventional standard means that we're using today. And so obviously this is very exciting because what you're doing is you're bumping up against the ultimate limits to processing information where the only kind of constraints are hardwired into the laws of physics. And so in a way, you're kind of using the language of nature. You're working with nature to actually perform your computations, your communications, cryptography. So what we're at now, it seems to be a whole dawn of a new era. And this is the era of quantum information, which we think will be incredibly, incredibly powerful and transform society in ways we can't even imagine. And to give you a little glimpse into how that might happen, you'll know about a bit. A bit is kind of the fundamental kind of unit of a computer. And over there on the left, we see there's an up arrow and a down arrow. And what they represent is a bit can only be two states, a 0 or a 1. But I'll show you a short animation now. A quantum bit, the analog, can basically be at any single point around the surface of that sphere you see. And so there are infinitely many points around the sphere. So there are basically kind of hopefully that shows that basically the kind of the realm or the domain of quantum physics and quantum information opens up many, many new possibilities we're only starting to glimpse of. And we're incredibly excited about this because, as I said, almost certainly it will transform society, transform technology in ways we can't even imagine. And to show you kind of where that is going, where we've gone so far, I'm now going to hand it over to Maitan.
Thank you very much, Damian. That was very nice. So what I'm going to talk about for the next few minutes is actual application of quantum information. So yes, it's a new field. Well, it's new, but it's been going on for almost 20 years now. But we're really just at the cusp of being able to harness the quantum world and build technology. So our main goal is to develop application and build devices that actually harness the quantum world and allow us to do things that are either faster, better, stronger, or even do things that were pretty much impossible with today's technology. Our long-term goal is the quantum computer. If we can build a full-fledged, scalable, fully programmable quantum computer, it will have a tremendous impact, and I'll be talking about that in a minute. But along the way, we are actually building techniques We are learning how to speak to atoms. We are learning how to listen to atoms. And that actually gave us a lot of tools to build other type of technologies. And some of them that I'm going to talk about is technology that has to do with sensing, other one that has to do with quantum communication, and also quantum materials. And all those applications can have a tremendous impact in the near to medium term and, of course, the long term. So the first one is quantum computing. If we can have a computer that works with quantum bits, as Damian explained, which are 0, 1, or any superposition of zeros and ones, turns out we can process information in a completely fundamentally different way and do things that are impossible. The first thing that comes to mind for me as a scientist is the idea of quantum simulation. And quantum simulation is very important because there's a lot of things that we do right now, and I'm thinking drug design, nanotechnology, material, where we're a bit in the dark. You know, we understand what's going on, but not fully, because we don't have the ability to go on our computer, program something, and then simulate what's going on. If you want to simulate a molecule, this is extremely hard. Take all the computer on Earth, and you won't be able to simulate past the element number 4 on the periodic table. So try to imagine simulating a full molecule with 120-something atoms on it. It's almost impossible. If you build a computer that actually behaves according to the laws of quantum mechanics, turns out you can simulate other quantum systems very efficiently and very easily. And that has a lot of application for material, for chemistry, biochemistry. And I'll give you a concrete example of the material side. Superconductors. Superconductors are those materials that carry electricity with no resistance whatsoever, no electrical loss, no heating. The problem is nowadays, if you want to have a superconducting gizmo, you have to cool it down to below minus 100 degrees Celsius. So it's not very practical. Why is that? Well, there's nothing in nature that tells us that a superconductor has to be cold. It's just that we don't completely understand how superconductor works. We have some theory, but the theory doesn't tell you how to do things. It just tells you how things behave. You have to simulate it. And we cannot simulate that. It's just way too complicated. So now we're just stuck at kind of trial and error, trying to find out, decent materials. A quantum computer will allow us to actually understand, simulate, build a superconductor from ground up that could possibly work at room temperature. How would that be important? Imagine building a regular computer made of superconducting material, then there's no heating, you don't need any fan. What's the biggest problem nowadays when building computers? Is heating, is heat dissipation. So you could have highly efficient electronics. But also, think of the energy crisis. Right now, carrying energy from one place to another one has huge amount of loss. If you can carry the energy or the electricity at no loss, you can just build a plant where the actual energy is, either a solar plant or a hydroelectrical plant, and then bring it anywhere in the world for free, energy free. So that will have a tremendous impact on society. Another example is drug design. Why do drugs have side effects? Like, well, we don't really understand drug. It's not an exact science. Trial and error is observation-based, it's very good, but we cannot understand exactly how a drug interact with another molecule or an enzyme or a protein because we don't have the computing power. A quantum computer, because it behaves according to the same law, will be able to do that, and will be able to build drugs from the ground up. And there's also a whole other slew of mathematical problems that are very relevant that can be done on a quantum computer in exponentially faster. I'm thinking about optimization, brute force searching, things for scheduling, artificial intelligence. Those are all the type of problems that we know today that will be more efficient on a quantum computer. And there's a whole bunch of problems where we still don't know. So it's really just the tip of the iceberg. So, quantum computer is great, but how do you build a quantum computer? Is it just an idea? No. We have prototypes. If you come to our lab at IQC, we have about 5 or 6 different types of prototypes. It all starts with the qubit. Qubit is any quantum system that have at least 2 different states, one for a 0, one for a 1, that behave quantum mechanically, that you can control, that you can measure, and you can make multiple of them interact with each other. Essentially, think of just a classical computer, but that work with the laws of quantum mechanics. There's pretty much 3 types of quantum bits. And there's multiple paradigms to do quantum computing, and the jury is still out of which one is the best. So we are looking at all of them, because all of them has advantage, they all have disadvantage, so we're still at the searching part. So the first system is what I call a natural system. Is what is given to us by nature, like molecules. We can control molecules, atoms, ions, photons. Those are really great because they're simple. There's only one of them. They're easy to understand. They're fairly easy to manipulate. If I tell that to a grad student, they'll probably kill me if I say that. But they're not too complicated. The problem is they're very hard to scale up because they come from nature, and nature does not always agree with what you think. The other one is the engineering system, the engineered system. Using the same type of fabrication techniques that we use for building microprocessors or typical computer, we can actually build system where we can push them to their quantum limits. A couple examples of this is actually on that picture there. This is an indium arsenide nanowire. This is a semiconductor. And by using electrodes, we can actually trap single electron along that wire. And we can use those electrons and manipulate them and make them behave according to a given algorithms. We can use superconductor circuit, where you just create a loop of current. And your current can go clockwise and can go counterclockwise, or can go in a superposition of both of them. And then those are engineered systems. They're very complex. The physics is quite hard. But because it uses fabrication techniques that we've been developing for 60 years, they're extremely versatile and have a huge potential for scaling up. And then there's the hybrid system. The hybrid system is a mix of natural qubit and hybrid qubit, where we're trying to leverage the good of each and try to get rid of the disadvantage. So the state of the art, at the moment, we can control, universally control, which means that I can do any algorithm I want to about on a dozen of qubits. So 12 qubit, it's not quite enough to build to beat the classical computer. You need about 35 for that. But 10 years ago, we were not even barely able to manipulate 1 qubit. Now we have 12. And trust me, controlling one single quantum system is not a walk in the park. It's extremely, extremely challenging. Let me give you an example of something we think we can do in the next 3 to 5 years. We want to reach 100 qubit. And we truly believe we can do that within 5 years. And now 100 qubit, we are already going in a realm where there's no way for us to actually simulate using a regular computer. So if you look at that molecule, it's called perchlorotrifluorine methane. There's a whole bunch of carbon. So there's the red and the blue. The red, forget about them for now. It's just to play tricks. That molecule has 6 quantum bits. We can control each individual carbon using an extra lying electron on the middle carbon. So the nuclei, the carbons are great quantum bits. They all have a small magnetic field. They can point up, they can point down, or they can be in both at the same time. But they're very robust, but they're very slow. By using the electron, we can actually control them directly without never really talking to the nuclei. We just talk with the electron, and we can control them about 1,000 times faster. Now what we do is we take that molecule, and we can grow a small matrix 4 by 4 with 16 of them, and by playing the tricks that I was talking about with the red nuclei, we can actually address each and every one of the nuclei in every one of those squares separately. And that one is actually, and that matrix is put in a superconducting microresonator, which is the picture on the right, that we can use to create the microwaves to actually manipulate the electron and also read out the state of the system. The control has been proven to work. The microwave cavity is working pretty good so far. We can grow the material. Now it's really just a matter of putting everything together. So we think between 3 and 5 years, we will finally have a quantum computer that will outperform for certain tasks any type of computer on Earth. Which brings me to my next part, quantum sensor. So, a 100-qubit quantum computer will be very practical, but we're not changing the world just yet. But along the way, as I was mentioning, we're learning how to talk to atoms. We're learning how to listen to them. We're developing techniques to deal with errors. We're developing control techniques. And that can be used for other type of technology. And the sensing one is perfect for quantum technology. A quantum bit is very fragile. Every time it actually interacts with its environment, it induces error and kind of kills the quantumness of your system. So we can actually turn that into an advantage. We can use that sensitivity of those quantum systems to actually sense the environment at the very small scale or at the very small quantity. This is the idea of quantum sensors. And when you really think about it, because we build devices that use the ultimate laws of nature, then technically we can build sensors that are the most sensitive, precise, selective, robust, efficient that nature allows. So this is the idea of quantum sensors. Some of them that we've built already. And by the way, quantum sensors, they're happening right now. It's a short-term to medium-term goal. One of our guys actually built a magnetometer using a superconducting qubit that can sense fluctuation in magnetic field to the tens of picotesla. This is about 1 order of magnitude better than any type of magnetometer you can find on the market right now. And that's just the proof of principle built in a lab. What are the use for this? Well, huge use for nanotechnology. Knowing what magnetic fields are at the very small scale is very powerful for nanotechnology. Really good for material science. Another example is another one of our guy. He actually used this to build a quantum sensor that is currently used for natural resource exploration. He used ideas of quantum information that we developed to deal with errors, and now it's been used in the field to sense. They drill a hole and they go find if there's ore or oil or any type of natural resource. And he's been able to increase the imaging part from 2 inches outside the bore to about 6 inches. That might not seem that much, but for a resource exploration company, this is hundreds of millions of dollars of saving a year. And that one particular company actually invested already $500 million into mass producing that technology. So those are things that are happening right now. And let me give you an actual concrete example. Diamond. Any one of you here that are wearing diamond, you might not realize it, but you're wearing a beautiful, well-behaved, simple, room temperature quantum processor. Actually, not the diamond itself, but defects in diamond. A pure diamond looks like nothing. It's pretty ugly. When the diamonds spark, this is because there's defects. Okay? Diamond is a matrix of carbon, but every now and again, there will be some carbon missing. And the defects that we particularly like is when there's 2 carbon next to each other that are missing, and one of them is replaced by a nitrogen. We call that a nitrogen vacancy center. This provides us a beautiful, very versatile quantum processor, and again, at room temperature. It allows us to bring magnetic field into spin, spin into light, chemistry into light, and so on. So we can detect electric field, magnetic field, chemical properties. And the beauty of diamond is that you can make them extremely small, but also they're non-invasive. You can implement them in the human body. You can implement them in cells. You can implement them in the brain. You can swallow them. You can actually chemically code them so that if you swallow them, they're going to go attach to a given enzyme or a given protein, and then you can start studying those in a non-invasive way. Right now, it's being used for measuring temperature gradient within cell. We can implement a small nanocrystal of diamond in a cell and measure the temperature within 10 nanometer within that cell. It has actually been used in the brain to measure the magnetic field of neurons, to do a full brain full mapping of the brain or the activities within the brain. This is a concrete example of what's going on. And also the beauty with diamond is that we can actually build them. This machine is a machine that can build diamonds on demand with a very controllable concentration of NV centers in it. And if you guys are interested to see what an artificial diamond looks like, I got a couple right here if you want to look at it. Which brings me to my next point, the idea of quantum materials. If you come to our lab at IQC, you will see big magnets that takes an entire room. You will see fridge that cooled down our system to fraction of a degree above the absolute zero. Because we need those conditions to see quantum effect. We need extreme condition. But again, nothing tells us in nature that you need that. Nothing says that you have to go down to 10 millikelvin to see quantum effect. Nothing says that you need 25 Tesla magnetic field to see something. And the idea of quantum materials is really what's going to bring quantum technologies from the laboratory setting to the marketplace. Quantum materials are those materials that shows very exotic properties that we wish to harness that will allow us to build very robust quantum technologies without the need of big equipment. I'll give you an example, the topological insulator. Topological insulator is a type of material that for some reason, if you pass the electric current in one way, all the magnetic field of the electrons goes up, and if you pass it the other way, it goes down. So what we're trying to achieve is that machine on the right, it's a brand new lab that was opened 6 months ago, very unique in the world. Within this, and this is a hunk of metal. It's 40 foot long. It has 5 different chambers. We can grow magnetic metals, non-magnetic metals, semiconductors, superconductor, topological insulator, oxides, all within the same machine without ever breaking current, without ever breaking vacuum. And that what allows us to do is we can build layers of different materials on top of each other. And in physics, it's not in the bulk that the interesting thing happens, is on layers. So when you go from one material to another one at the interface, this is where the cool physics happen. And what we're trying to do is we're trying to engineer materials with the quantum properties that we need to actually build our devices in a self-carrying, in a self-contained way. Some of the materials that are already working on, there's material out there that can create their own local magnetic field up to 50 Tesla. Keep in mind, the biggest magnet ever built by humans is 45 Tesla. So just by building the right material, you can beat that. And those are the things that we are looking for. One last thing I want to talk about is quantum communication. If there's any people in ICT field here, you will be interested by this. So if you project yourself down the road a little bit, you might think of having a whole bunch of quantum computers around the world. You will have to communicate quantum information from one place to another. So the quantum internet. That's something that we're working on. But also, quantum information gives us an edge for actual classical information. We can harness quantum effects to enhance, so to turn, let's say, a noisy communication channel into a noise-free communication channel just by using quantum entanglement or other type of quantum effect. We can do authentication. we can do secret sharing. But the one that I want to focus on is the idea of quantum key distribution. If you were here earlier at the session at 10:30, my colleague Mike Mosca talked about that a little bit. So the idea of quantum key distribution is to harness quantum mechanics to actually help us create information security in an absolutely unbreakable way. At the basic of any information security out there is a hard mathematical problem. All the security we have nowadays is based on a hard-to-solve mathematical problem, which means that any advance in computing, i.e. quantum computing, makes those security not secure anymore. And we are confident we will build a quantum computer. And as we know today, there are no systems that are quantum safe. So everything out there is potentially a risk. But remember what Damian was explaining, the uncertainty principle. The uncertainty principle says if you're trying to measure a quantum system, you perturb it. So what we can do is we can use photon, particle of light, that behave quantum mechanically. We can use this to try to establish a secret key between two parties such that any attempt at eavesdropping will be detected. And the security is ensured not by mathematics, but by the very laws of physics. You want to break the communication, you have to break the laws of physics. And as a physicist, I can tell you, you can't. And the beauty of quantum key distribution, it's already here. We have it. There are companies out there that sells you system. Like if you look the picture on the left, this is a system sold by a Swiss company called ID Quantique. The two black boxes at the bottom, those are the quantum key distribution box. This is one end that we call Alice. There's another of those black boxes somewhere else, and they can, up to about 75 kilometers, they can exchange constantly secret keys that are untampered with. There exists a few small networks in the world. The one picture that you have here is the latest one, is the one in Tokyo with 4 nodes. There was one in Boston that was built in the mid-2000s. There was up to 10 nodes. At some point, there was even a very small one between the IQC and Perimeter Institute. There was only 2 nodes. Okay, we just live down the road, so we can just ghost each other for sharing secret, but we had a quantum cryptography lane going between the 2 of them. Unfortunately, nowadays, we're stuck to about up to 75 kilometers because a single photon that you send will be absorbed by fiber optics. How do you turn that into global quantum key distribution? What if I want to talk with my friend in Australia? Well, the idea is to go to satellite. If I can reach or establish a secret key with a satellite, then I can have my secret key, the satellite goes somewhere else, share another secret key, and effectively the 2 places are linked with that secret key and then can do unbreakable security. This is a project that is going on right now between IQC, PI, the Canadian.
Your attention. In the Vision Theatre, starting in 5 minutes, will be the presentation by Betty DeVita, President of MasterCard Canada. Please make your way to the Vision Theatre.
So between PI, IQC, the Canadian Space Agency, ComDev, Communitech, and a few other Canadian universities, within 3 to 5 years, we think we can launch a satellite. All the proof of principle has been done. Now we're really at the engineering part of putting everything together and then launching it. So I'm going to conclude here just to remind you that really quantum mechanics give us a very rich environment to process information in a fundamentally different ways. Applications are they're numerous and they're varied. And just like what happened with the Silicon Age, the quantum age would be transformative and will really have an impact and sooner than you may think. And really at that point, it's really just our imagination that stops us from knowing where we're going. Thank you.
Thank you very much, Martin. Thank you, Damian.